Sealed within our machines and structures is a substance that is essential to their functioning. This hidden ally makes them stronger, cheaper, lighter, even sexier. And it's the least sexy substance of them all: glue. Like Superman's alter ego Clark Kent, glue goes about its duty unnoticed. But when called upon, it can exhibit superhuman strength.
A properly used adhesive is not apparent to the person using whatever it is. You don't see it, so you don't know it's there, and therefore you don't have a reason to appreciate it.
If we know anything about glue, we know that it needs to be strong. To test this, we're going to stack the odds against an adhesive, Mr. Sticky's underwater glue. Not only will the glue have to hoist this truck up off the ground,
on top of that, the lifting device that we're going to use, which we have right here, is going to be bonded completely underwater. And we're also going to be applying the glue underwater.
This underwater glue is an epoxy, a category of glues that have a catalyst and a resin, which combine during application to chemically react and cure. The adhesive is designed to be applied to wet or dry surfaces, or, as we have chosen, to something totally submerged in water.
There are no parts.
But wait, who needs an underwater glue anyway?
While there are a number of direct underwater applications, repairing your pool, putting tiles on underwater, fixing main drain covers, fixing gutters, we've actually had some great successes in terms of bonding coral and repairing coral reefs. The reality is that many substrates have water as part of them.
Does this underwater glue have the strength to do the trick? Stick around. You'll see what a little glue can do. While glue's strength may be its most dramatic characteristic, its omnipresence is equally impressive.
From the time you get up in the morning to the time you go to bed at night, you must touch things that have adhesives in them probably every 5 or 10 minutes. I mean, there really isn't an industry that adhesives don't play a part, whether it's construction, medical devices, surgical adhesives, automotive, electronics, transportation, bookbinding, packaged goods. It's really everywhere.
But what would life be like without adhesives? Imagine for a moment the room that you're sitting in, without glue. Virtually nothing around you could stay together. Furniture, wallpaper, carpeting, even the plywood in the walls would come apart. TV, VCR, cell phone, DVDs would be reduced to a pile of parts. Shoes, envelopes, pens, useless. Crowns would fall off teeth. And watch out for that baby. His diaper's about to disintegrate. Glue is everywhere, and it's more than a $20 billion a year global business. The industry sells adhesives manufactured from animal or plant derivatives or synthesized from petroleum. Whether natural or synthetic, glues are made up of polymers characterized by their high molecular weight, which give them their strength.
If you start with a chemical unit, a single one chemical unit, which we refer to as monomer, mono meaning one, right? We have one unit. If we take a bunch of these one units and hook them together, you create what is called a polymer. You have one stick, I give it to you, you go, you can break it. I give you a bunch of those same sticks together, they don't break. The reason why they don't break is because together they have formed a tougher, more resilient animal.
Glues stick in two ways: mechanical and chemical bonds.
One is a mechanical interlocking, in which molecules get tangled up with roughness in the surface. Sort of in the same way that when you bring two pieces of Velcro together, one is hooks and one is loops, and they get tangled up. The other is through chemical interactions. There can be very strong covalent bonds in which there are two atoms linked together to form a very strong bond that's very difficult to break.
Glues have been holding their own for thousands of years. The earliest were natural, derived either from plant sources or from animal protein. Hide glues, which get their adhesive properties from collagen, the main protein found in animal skins, were probably discovered when ancient peoples found they could bond tools, weapons, and pottery using the sticky protein residue found at the bottom of their cookpots. The collagen, which is rendered during cooking, forms a strong bond by soaking into porous surfaces like wood and hardening during cooling and drying. A casket removed from King Tut's tomb was sealed with animal glue. The word glue traditionally referred only to these hide glues, but the modern term for glue is adhesive. Both glue and adhesive refer to a substance used to stick two surfaces together. Other early glues were made from tree sap. Sticky resins were collected from trees, applied as is, and allowed to dry to form a bond. The Romans were one of the first peoples to glue together and waterproof their ships with adhesives made from a blend of tar and beeswax. This effective mixture combined the stickiness of the tar with the waterproof qualities of the wax. By the 19th century, there was widespread use of starch glues to bond paper, and particularly wallpaper. Mixed with water, starches derived from wheat, rice, and corn develop into a highly viscous, sticky paste, which soaks into porous papers or cardboards and bonds when dried. By the 20th century, animal glues were being mass-produced from rendered cattle hides, a byproduct of the beef industry. During the manufacturing process, the hides are washed, soaked, shredded, and boiled to extract the gelatinous collagen. This material dries into sheets and is then ground into a powder to which water is added for use.
These were protein glues extracted from hide, and they're still very important. The classic furniture restorers, for example, still swear by hide glues because they're the only thing that will bond to the old glues.
Today, 3 U.S. producers of animal glue remain, including Milligan and Higgins. Because of its flexibility, the product has become a specialty glue used on guitars, organs, and veneers. By the 1930s, the development of synthetic adhesives, which had quality and consistency advantages over natural glues, revolutionized the industry. These new adhesives were offshoots of the first synthetic rubbers and plastics.
All the major developments have really come about in the last 100 years, which really coincides with the development of materials from petroleum feedstocks.
The growth of one company, National Starch and Chemical, mirrored the changes in the industry. Founded in 1895 by Alexander, the company's product line was dominated by starch-based adhesives.
The predominant adhesive in those days was the starch and dextrin-based adhesives. And they were used for all of these applications, making envelopes, making bags, making tubes, making cups, sealing cases. Over the years, it began to change from those natural-based materials to synthetic. When you use natural-based products based upon starch or dextrin, it would take maybe 50, 60 seconds to develop a tearing bond. Then synthetic products, polyvinyl acetate came along, and maybe you could get a setting bond in 10 seconds.
By the 1950s, the company had developed a proprietary method of producing vinyl acetate, a latex that resulted from plastics research, and was on its way to diversifying its adhesive portfolio. From its humble beginnings selling wallpaper paste, National Starch is now a worldwide $3 billion a year global adhesives company that sticks the labels on food packaging and holds cars and computers together.
The starches and the gelatins and the animal glues had good properties when you were sticking things that were natural, like wood and paper, but did not fit in the world where you now wanted to stick first metal and steel and iron, and now a wide variety of sophisticated plastics and composites.
In 1947, as synthetic glues were coming into vogue, Borden's Elmer's division introduced Elmer's Glue All, a synthetic glue that featured that familiar logo.
Where Elsie was the food side of the business, Elmer represented sort of non-foods, and it took off. It was wildly successful, and in 1967, we actually launched Elmer into the school market. That's when we brought out the Elmer's School Glue.
Elmer's had another marketing coup in the 1970s with Crazy Glue, an instant glue that forms bonds on just about anything.
A plastic knob or rubber boot, model planes and model trains.
And unfortunately, fingers.
If you bonded your fingers together, I'll give you a little clue as to how you get your fingers apart. Don't try to rip them apart like this, because you will rip the skin. What you do is take a pencil, or you can take your finger even, and roll it so that you start to peel the adhesive off of your fingers.
Some of you may recall the advertising in the early 70s that had a man with one drop of glue and then was hung from a hard hat and a crane.
Crazy glue, strong enough to hold this man suspended in midair.
Well, that image, even today, more than 30 years later, is still recognizable and is remembered.
And that image inspired Art Quinn, CEO of Advanced Adhesion, to attempt an act of brazen one-upmanship for modern marvels. He took his glue, Mr. Sticky's underwater glue, and applied it to a steel fitting that was immersed in water. After letting it cure underwater, Art's going to use that glue bond to try to lift a 3-ton truck. First, the guys have to secure 6,000 pounds of pickup. It's time for the lift. Let's see if Mr. Sticky's can live up to its name, or if 3 tons of truck are going to tumble to the turf. The wires are tight. We've got liftoff. Every ounce of weight is pulling down on the adhesive, but it's gonna hold.
I'm a happy guy. It's done the job. Fantastic.
Don't try this stunt at home, but if you're gluing something a little more down to earth, we've got construction glues that would sooner tear apart steel than give up their grip. Throughout the world, the manufacture of plywood is the single largest application of adhesive. It's one of many construction components that are assembled with adhesives before they ever reach the construction site.
Conventional wood has a grain to it, so it tends to be strong in one direction and weak in the other. If you laminate them together in commonly 3 or 5 plies, as it's called, you actually get a material that's stronger than the original wood.
Increased strength is accomplished by laminating the layers at right angles, so that the wood grain runs in many directions in the plywood. The plies are then bonded with a phenol formaldehyde resin.
Adhesives are applied to the wood, and then the wood panels are pressed under high pressures and high temperatures to actually cure the adhesive.
Phenol formaldehyde is a combination of phenol, a derivative of coal tar, and the preservative formaldehyde. This low-cost adhesive is used in manufacturing boards made from wood particles, as well as in plywood. Throughout history, humans have used glues in making shelters. 2,500 years ago, Nebuchadnezzar used natural tar, a petroleum resin, in the construction of buildings in Babylon. And the Aztecs used a cement and blood adhesive mixture that's still holding the remains of their structures together. Today in our modern homes and offices, we're surrounded by a variety of specialty glues that are often stronger than the materials they're holding together. A simple test of a wood glue bond, in this case Elmer's glue, demonstrates the strength of the bond versus the substrate, the wood.
Good wood glue should have not only good strength, and in this case you have around 3,500 pounds per square inch, but a good wood glue should also have what we call substrate failure. In this case, the wood was actually pulled apart, which means the glue was actually stronger than the wood itself.
All right, so what I'm going to do now is a dowel joint.
In a dowel joint, small wood fittings or dowels are glued into drilled holes. With the help of wood glue, they hold the joint together without nails or screws.
These will be used for picture frame, door frame, furniture, anywhere you don't want to see an exterior fastener where it's going to have to get patched. So, and it's great, it's strong. The holes have been drilled. We will now apply the glue. Just a little dab will do you. Tap it in, put it together, clamp it tight, clean up the glue, set it aside. That's it.
Not all woods are created equal. Rubber woods in the Far East are denser and oilier than maples and oaks. These woods are used to make furniture, plywood, and parquet flooring.
And the adhesives that we use in this country just do not work properly on those woods. So a new line of products had to be developed to satisfy the woodworking industry, a lot of which had moved to the Far East.
Another construction process, painting, relies on a different type of adhesive, masking tape. Painters use tapes to paint within the lines. This hardware store staple was the brainchild of 3M inventor Dick Drew, who noticed that automotive painters were having trouble making sharp lines on the two-toned cars that had become popular in the 1920s. Drew developed a product that created an impermanent bond, a pressure-sensitive masking tape.
And he was able to come up with a product that was permanently and aggressively sticky, but removable at the same time.
Pressure-sensitive adhesives have a split personality.
You have to imagine the material neither being a liquid nor a solid. It is something else in between. And we call that material a viscoelastic material. That means it has viscous properties like a liquid, but it has elastic properties like a solid.
Tapes soon found other applications. In the 1930s, Drew went on to coat samples of cellophane with 3M adhesive to invent Scotch tape.
Dick Drew made notice of the fact that people were starting to use cellophane as a means of packaging foodstuffs. And he thought, wouldn't it be wonderful to have a cellophane-backed tape which one could apply to that cellophane, have it stick, and of course be openable later on.
3M, Drew's employer, was founded in 1902 to produce sandpaper products. Today it offers a full line of adhesives designed for everything from seats to signs to versatile Post-it notes, known for their ability to be stuck, unstuck, and restuck. A repositionable glue like the Post-it notes is a far cry in terms of strength from this construction adhesive, developed at Henkel. A reactive two-component room temperature curing adhesive system. This glue is especially designed for galvanized surfaces. When subjected to thousands of pounds of pressure per square inch, the steel will tear before the glue fails.
This is 16-gauge steel, okay? And look what we've done to the 16-gauge steel. The adhesive is completely intact. Look what we've done to the steel. We've actually ripped the steel. And this happens at about 5,200 to 6,000 pounds. Okay. One of the major deterrents to using light-gauge steel in construction today is the cost of making the connections. In order to get the proper load distribution, you have to use a lot of screws. Using our adhesive system, you're talking about saving 80 to 90% of the labor cost.
At ITW TAC, labor savings is just one of the considerations for its adhesive systems.
Subfloors are made up of plywood bonded to the joists. When you put the bead of subfloor adhesive on the joists, drop the plywood in place, and then screw it down, what that does is it fills any of the voids, and it also has a little bit of give to it. When the wood is expanding and contracting with the seasons, it's going to help that not squeak.
Overhead, a ceiling can be held up by a two-part polyurethane foam without the help of screws and nails. As the adhesive is applied, it mixes and reacts, foaming to fill seams and hardening as it cures.
This was a revolutionary application that was developed for manufactured housing in the late 1960s. It allowed manufactured home builders to create a finished ceiling panel without the use of any mechanical fastener.
Another fast-acting adhesive is found inside countertops.
Countertops are typically put together with a contact adhesive. That's where the wood substrate, the particle board typically, and the high-pressure laminate each get a coating of adhesive. When that film is dry, in 2 to 5 minutes, the bond is made, and it's an instantaneous bond.
At home, you're surrounded by glue. But if you think you can get away from it by leaving, think again. Whether by land, by sea, or in the air, glue is on the move. Cars and boats to planes. If it goes with glue. The trend in the automotive industry is typical of the transportation sector at large. Advances in the materials cars are made of have transformed the way they're held together. The first cars were made from one material, steel, and held together with welds, bolts, and rivets. That's no longer the case.
Your car's composition, which used to be predominantly, steel, has moved a lot towards things like aluminum and plastics and urethanes and synthetics as well. And that evolution, driven by weight reduction in many cases, as well as cost, has really opened up the ability for adhesives to be used in the assembly of cars.
Adhesives provide excellent bonds between dissimilar materials, fill and seal cracks, and don't fracture more brittle composites, as a mechanical fastener might. One of the key adhesive applications in a car is around the windshield.
Front glass and the back glass are both urethaned in, so that's where part of the structural support, because as you can tell nowadays, the metal's nowhere near as thick as it used to be. So a lot relies on the glass holding the roof up in a rollover.
During a windshield replacement, you can see how strong that urethane bond is when you try to remove it.
This will cut the glue that's in here, which is usually about a ½ inch, maybe 3/4 inch wide.
Once the broken windshield's out, it's time to apply the glue. 175-degree urethane, which cools and cures quickly.
We got about 8 minutes to get the windshield in. We want to get in there as quick as we can. So it'll be about an hour before they could drive away safely.
When the adhesive is thought about in the front end of the design, it's providing lighter weight, less parts, ultimately less cost. There's a lot of labor involved with drilling a hole, placing the rivet, and making that component adhere to one another.
A key breakthrough to replacing mechanical fasteners occurred in 1953. Chemist Dr. Vernon Kriebel of Hartford, Connecticut, solved the instability problem of a new adhesive that his chemist's son, Robert, had brought him. Vernon Kriebel developed a cure inhibition system for a unique liquid bonding resin that hardened anaerobically, or in the absence of air.
As long as it's in contact with air, it remains a liquid. You put it onto a nut and bolt or onto a bearing or any shaft-mounted part, and what it does is it wicks its way between the threads. As soon as it's in the contact of metal and there's no oxygen for it to remain stable, it hardens to essentially a tough plastic.
The product, Loctite, solved the problem of loose nuts and bolts in machines and appliances, and is still the cornerstone of the company's adhesives business. Loctite products can be found in many of the cars on the road. But the adhesive's usefulness is most dramatic in high-performance vehicles, where vibration is intense and you can't afford to have a screw loose.
The Daytona 500, virtually every one of those cars is held together, the threaded parts especially, are held together with Loctite thread lockers.
In the 60s, part of racing was cleaning the track up, and they would literally go around the track and with a sweeper and clean up nuts and bolts that may have come off during the race. If you look at Formula One or NASCAR, these adhesives widely used are gasketing silicones, thread lockers, retaining compounds. These again are being used to be able to provide a quality race car that's not going to have loose fasteners, that's not going to have gaskets that are going to leak mid-race.
Similar considerations are just as crucial on streets and highways. During any given rush hour, there are literally tons of adhesives on the road. A car's door panels held in with an adhesive. The seats foam laminated to their coverings. The dashboard components, multiple layers with adhesive laminates. The headliner, a vacuum-formed laminated material. The rear view mirrors held on with an adhesive. Air filters, rubber trim, and gasketing contain glues. And of course, there are adhesives in the computers that increasingly run the automobile. Headlights and taillights, adhesively sealed to keep water out. Pinstriping and side molding, held on with high-performance pressure-sensitive adhesives. Even the tires are layers of adhesively bonded materials.
The friction surfaces that are inside the brake linings, those are also adhesively bonded on. So you might even be able to say that adhesives help your car go and adhesives help your car stop.
And as you pull up to that stop sign, you may well be looking at a product bonded by tape giant 3M.
Many of the reflective signs that you see on roadways are generated by 3M. The sign itself is attached by means of a pressure-sensitive adhesive in many cases to the sign backing, which is very often aluminum. Many of the reflective pavement markings that you see are generated by 3M, and you could think of these things as basically pavement markings on a roll. They take a very large roll of tape and apply to pavements in order to provide a temporary lane marking that people use in construction zones.
But once you leave land and get out on the water, the demands on glues increase.
You see saltwater environments, and you've got to be able to provide an adhesive that can fill a large gap, provide structural integrity, and provide a very rigid assembly that can take impact.
Traditionally, the interior structure of a boat was made with hundreds of pieces of wood that had to be stapled together. With the help of adhesives, that process has been replaced by a composite construction.
And what a manufacturer will do that's using plexus adhesives to bond a composite grid in is they basically lay the adhesive down into the hull of the boat. They lay the stringer system down into the hull, they let it cure, and the assembly process is done. They're able to eliminate over 250 different parts that it took to assemble the wooden egg crate configuration and combine that into one simplified structural grid made out of composites.
It takes a surprising amount of glue to make a boat.
When we're done bonding this boat, there will be between 30 and 40 gallons of adhesive used to bond the structural grid.
Some of the largest glued surface areas of all can be found not on land or in the sea, but up in the air.
You want to make an airplane. It's got to be lightweight. It's got to hold in air, okay? It's got to hold out the environment. How do you do that all in one shot? And the way you do that is by adhesive technology.
Much like cars, planes have featured the battle between glues and rivets. Aircraft adhesives were originally developed in the 1940s, but it wasn't until the 1970s they were used widely in the large-scale bonding of aluminum aircraft structures. Today, adhesives have made it possible for as much as 50% of a new airplane to be constructed from lighter and more efficient composites, made by blending multiple materials like plastic and fiberglass.
Joining composite sections together is virtually impossible by mechanical fasteners. You really have to join these things together by adhesives because mechanical fasteners just stress them too much. If you talk about the actual fuselage or the wing skins or the flaps, those are almost always made out of an epoxy adhesive. Very high strength, high performance epoxy adhesive. And basically the technology that goes into those is right at the top of the line.
Much of an airplane is composed of a sandwich fabricated from aluminum with a honeycomb core and panel skin. The honeycomb structure is adhesively bonded together. Inside the cabin, storage bins are glued together, the floors are bonded, the covers on the seats are glued to the cushions. Sealants are applied to keep out moisture, maintain cabin pressure, prevent fuel leaks, to weatherproof the airframe, and to situate and seal electrical connections and cables. Airplane adhesives are among the toughest because the cost of failure is so high. Where space travel is concerned, a new adhesive may prove instrumental in preventing another shuttle disaster. From trips to outer space to the inner space of electronics, adhesives play an indispensable role and might just turn out to be lifesavers.
And hang on, where you guys at?
On February 1st, 2003, the Columbia Space Shuttle broke up as it attempted to re-enter the Earth's atmosphere. killing all 7 astronauts on board. The disaster was caused by a hole in the carbon-carbon composite panels that form the leading edges of the craft's wings. The hole allowed the extreme heat of re-entry to penetrate the craft's heat shielding.
When it was re-entering, the hot gases were going into the hole and it was melting the metal inside as well as destroying the carbon-carbon outside.
Scientists at NASA are designing a repair system so that if damage is detected, it can be repaired while in orbit. One material tested for this purpose is a ceramic adhesive called Grabber. Blend refractory adhesive for bonding and exterior repair. Grabber would be used to fill cracks, but it would have to withstand some pretty tough conditions. During re-entry into Earth's atmosphere, temperatures on the leading edge of the shuttle reached 2,960 degrees Fahrenheit for about 12 minutes. Grabber, which converts from an adhesive to a high-temperature ceramic during re-entry, underwent harsh tests at NASA. Carbon-carbon composites repaired with Grabber were submitted to 1,650 degrees centigrade temperatures for 12 minutes.
After almost 10 minutes into the test, the reinforced carbon-carbon disc material, which is a substrate, it started failing, burning near the holders. But there was nothing wrong with the crack repair material. All the material is still intact.
Grabber would have to be applied by a spacewalking astronaut using an oversized caulking gun, sized to fit the astronaut's bulky gloves.
An astronaut really only has the dexterity of a 3-year-old. You don't have a lot of mobility in space. So you have to design it accordingly to what a 3 or 4-year-old could handle.
While applications may be slow and cumbersome in outer space, back on Earth, in the cutthroat computer industry, adhesives are turning gadgets into leaner, cheaper, tougher tools that continue to speed up our lives. Whether you're working on your 7th computer or your 17th cell phone, you've noticed that size matters. In the world of electronics, small is huge. One of the keys to electronic devices shrinking and becoming more convenient and versatile is the increasing use of adhesives in their manufacture. Adhesives replace cumbersome mechanical fasteners, encapsulate and protect ever-shrinking and more fragile connections, and dissipate heat on crowded circuit boards.
If you looked at the original cell phones, you look at the cell phones that we have today, one of the reasons they've gotten so small is because of adhesives. All the components that are on a circuit board that used to be mechanically held in place are now bonded with high-tech adhesives.
Computers, they're getting faster and they're getting more intuitive for the end users to work with. The customers are expecting adhesives to bond a variety of materials going from plastics, rubbers, and metals, and they're easier to use, faster curing, and can save the customer time as far as their assembly process.
Saving assembly time means saving manufacturers money. As a result, the global electronics adhesives market has grown to roughly $1 billion annually. Abelstick, a division of National Starch and Chemical, and Henkel Loctite are two of the biggest players in this arena. Before the advent of modern electronics, electromechanical devices such as motors and generators were held together with adhesives. Those adhesives have been purified for use in today's more demanding and delicate electronics. Electronic adhesives are expected to perform a variety of functions, beyond simply keeping it all together.
Without adhesives, you couldn't make the Pentium chip and the processor. That all has to be assembled together, and it has to be assembled together. It's not soldered and welded anymore. They're held together with some very, very sophisticated adhesives that balance the electrical conductivity and the heat management that goes with the information and the chemical purity to not have any interference with these very microscopic electronic properties that are going on.
A lot of the adhesives that we're using are more of an insulator, such as silicones or epoxy, so they're providing some type of protection to the printed circuit board. So if it's being used potentially underwater or in a severe environment, the adhesive is acting as a protective coating.
As well as protection, adhesives are providing conductivity. Gold and silver have been added to impart electrical properties so that they can replace solders. This is part of an industry-wide effort to get toxic lead out. Equally important to conducting electricity is conducting heat.
Getting rid of heat is important because when you put heat into small metal parts, it causes expansion and contraction, and movement is not good. So you're trying to manage the dissipation of heat.
The cramped quarters of a circuit board make it a breeding ground for heat. Thermally conductive adhesives filled with aluminum oxide have proven successful at drawing off and dissipating heat.
The microprocessor processes billions of instructions per second. Lots of electrons running through the circuitry every second, and that generates a lot of heat. Thermally conductive material is going to be used to bond the microprocessor to this cooling unit. And basically it's just a big fan that sits right on the back of the microprocessor, and it's going to plug right into this motherboard.
Membrane switches, essential to the functioning of computer keyboards, VCR, and microwave controls, are made from pressure-sensitive tapes.
The numbers that are on your microwave oven are subtended by layers of pressure-sensitive adhesive tape, some of which are die-cut and some of which are not.
These layers of flexible tape with die-cut interior holes allow users to press surface buttons and make a connection through to a circuit element concealed beneath the tape. While the market for electronic adhesives is growing as fast as our insatiable appetite for devices, scientists have developed an appetite for this tasty mollusk, or at least its submarine superglue. The words animal glue conjure images of boiled hooves and hides. But the future of animal glue is coming from an unlikely place.
It's quite amazing the range of surfaces to which mussels can stick. They can stick to metals, to rocks, to glass, even to Teflon, which we think of as a non-stick surface. And what I think is even more amazing is they stick to these surfaces when they're wet.
Researchers are attempting to understand the protein in mussel glue so that they can duplicate its properties.
Mussels have a small gland in the foot, and they secrete a very sophisticated cocktail, a composite in a liquid form, not unlike what spiders secrete. A structural stiffener, a protein like collagen, which we find in our bodies and ligaments and cartilage. But there are also these sticky proteins. The molecule seems to be in an extended helix shape. There are about 800 amino acids in the protein, and close to 200 of them contain these sorts of sticky sites. So that means that we have many possible adhesive interactions with the surface, and even though each interaction might be weak, we have a lot of them, so it ends up being very difficult to remove this protein from the surface.
Though this versatile glue is costly to harvest from mussels, $75,000 per gram, researchers have been able to use recombinant DNA technology to clone the protein's genes and transfer them to an inexpensive yeast. Researchers hope that this non-toxic, waterproof, natural glue will have commercial potential for construction, marine, and medical applications.
So what we're doing is we're studying how the mussels make their glue and figuring that out, and then we're using that to develop synthetic adhesives based on what we learned from the mussel.
An adhesive with proven medical uses started out as a superglue more suited to garage repair jobs. In the 1960s, Dr. Harry Coover, the inventor of superglue, developed cyanoacrylate sprays for use on the battlefield during the Vietnam War. The sprays closed wounds long enough for the injured to be transported and receive treatment. Today, Dermabond and Indermil, both cyanoacrylates, are used extensively in surgery and emergency medicine. Once wounds are closed with subdermal or under-the-skin sutures that dissolve with time, a cyanoacrylate such as Dermabond is applied to the surface of the incision.
One real benefit to Dermabond is that you eliminate any external sutures, so there's no chance of getting the little railroad tracks that we've all seen on incisions. It seals the wound, so it's got a barrier for infection, and in some areas of the body that we operate on, such as perhaps the inner thigh area, really has cut down on my incidence of infection.
A pig's foot is used to demonstrate Dermabond's application technique.
I'm going to make an incision here, and you can see down into where the fascia is down there. If there's no tension on the incision or on the laceration, we can use the Dermabond as our primary wound closure. So this is an ampule of Dermabond. I'm going to take the tension off my incision and put 2 layers of Dermabond. Here's the first layer. Here's the second coat. And then you have to let it dry for 2 minutes.
With Dermabond, and when you've sealed the wound, then you can have the patient shower. You're not worried about water getting into the wound.
Cyanoacrylates are also useful in the manufacture of medical equipment and small consumer devices. In a precision manufacturing setting, the glue's strength is an asset, but its instant cure can be too quick. The solution is an innovative light cure technology.
You can apply the adhesive to the surface, mate the 2 parts together. It will stay liquid until you shine an ultraviolet or a light on the surface. This gives the end user flexibility for manufacturing in high-quality components. Light cure adhesives, they're tailored to polymerize at a specific wavelength of light. This is an example of an LED light source, which is predominantly putting out in the 405 nanometer wavelength, which correlates to the adhesive being used.
Adhesives are found in other medical applications, like the transdermal patches that deliver nicotine and hormone therapies.
Skin is one of the most phenomenally changing substrates there is. No 2 people are the same. Your inherent ethnicity, your diet, your food, all changes on an ongoing basis the composition of your skin and what's on the surface. And what does this mean? This means you have an ever-changing substrate that you're trying to stick to.
But the adhesive does more than stick. It's also involved in the drug's delivery.
You have a controlled release that is directly related to the ability of the active ingredient to work its way through the adhesive mass into the skin.
From human skin to the skin of an airplane. From the minute applications in computers to the maximal amounts of adhesive pumped into boats. From the space shuttle to subflooring. Without fanfare, but with strength and versatility, glue holds our world together.